In this video, we're going to discuss the Maclaurin series for the function f of x equals e to the x. Recall that in general, the Maclaurin series for a function f of x is the series from n equals 0 to infinity of c sub n x to the n, where c sub n is the nth derivative of our function f evaluated at 0 divided by n factorial. In order to state the Maclaurin series for a function, we need to find a formula for the coefficients c sub n written only in terms of the number n. We can do this by finding the first several derivatives of our function f, evaluating those derivatives at 0, dividing by n factorial, and looking for a pattern in the resulting coefficients. So let's do this by finding the Maclaurin series for the function f of x equals e to the x. And once we have that Maclaurin series, we want to find its interval of convergence. We start by finding the first several derivatives of our function e to the x. And this is quite easy to do since e to the x is its own derivative. So f prime of x will be equal to e to the x. F double prime of x will be equal to e to the x. And f triple prime of x will be equal to e to the x, and so on. Each derivative will always be the same function in this case. Because we want the Maclaurin series, this is the Taylor series about 0, and so we want to evaluate each of these functions at 0. And so here we get e to the 0, which will be 1. F prime of 0 will also be e to the 0, and therefore equal to 1. F double prime of 0 will also be 1, as will f triple prime of 0. And in fact, any derivative of this function evaluated at 0 will always give us a value of 1. We then have our coefficients, which are the derivatives divided by the appropriate factorial. So we have c0 is 1 over 0 factorial, which is 1 over 1, or 1. C sub 1 will be 1 over 1 factorial, which is also 1 over 1, and is equal to 1. C sub 2 will be 1 over 2 factorial, which we could write as 1/2. And c sub 3 will be 1 over 3 factorial, which we could simplify to be 1/6. So now we want to look at these values of c0 through c3 and try to find a formula for c sub n by looking for a pattern. And here what we hopefully notice is that each of these is the number 1 divided by the value of n factorial. And so we can pretty easily see that c sub n will be given by the formula 1 over n factorial. And therefore, this is the coefficients for our Maclaurin series for e to the x. And so we can simply write our Maclaurin series as the series from n equal to 0 to infinity of our coefficient 1 over n factorial times x to the n. And if we'd like, we could combine those terms together to get the series from n equals 0 to infinity of x to the n over n factorial. And this will be our Maclaurin series for e to the x. We now want to find the interval of convergence for this Maclaurin series, and to do that, we approach it just like any other power series and use the ratio test. For the ratio test, we'd like to find the value of r, which is the limit as n approaches infinity, of the absolute value of a sub n plus 1, the n plus first term of our series, divided by a sub n, the nth term of our series. To do that, we just substitute in the values for a sub n and a sub n plus 1. So we have the limit as n approaches infinity of x to the n plus 1 over n plus 1 factorial. And then we'll multiply it by the reciprocal of our nth term, which will be n factorial over x to the n. And here, x to the n plus 1 can be rewritten as x to the n times x, and n plus 1 factorial can be rewritten as n plus 1 times n factorial. And so we get some cancellations here with the x to the n's and the n factorials. And so we have the limit as n approaches infinity of the absolute value of x in the numerator and n plus 1 in the denominator. And here with n getting larger, this denominator blows up with a fixed number of absolute value of x in the numerator, and therefore this limit is equal to 0 and is less than 1. Therefore, since this limit of ratio of consecutive terms is equal to 0 and is always less than or equal to 1 for every value of x, this tells us that our interval of convergence is the set of all real numbers represented by the interval negative infinity to positive infinity. So this particular Maclaurin series, n equals 0 to infinity of x to the n over n factorial, converges for every single real number x. If we put the two parts of the preceding example together, what we have shown is that for every real number x, e to the x is exactly equal to the sum of the series from n equals 0 to infinity of x to the n over n factorial. We can now use this series from n equals 0 to infinity of x to the n over n factorial just like we used the power series representation of any other function. For example, let's suppose we wanted to find the exact sum for the series n equals 0 to infinity of 5 to the n over n factorial. We could easily use the ratio test to show that this series converges, but the ratio test alone doesn't help us actually find the sum of this particular series. What will be helpful to find the exact sum is to compare it with the Maclaurin series for the exponential function that we just derived, namely the sum from n equals 0 to infinity of x to the n over n factorial. We can even write out a few terms for this particular series, which would be 1 plus x squared over 2, or 2 factorial, plus x cubed over 3 factorial, or 6. At this point, we should see a connection between the given series and the Maclaurin series for e to the x. In particular, what we're doing is simply evaluating the Maclaurin series at x equal to 5 to obtain the desired series in this example. And so here, if we take our Maclaurin series evaluated at x equal to 5, in each term, we obtain the desired series that we're being asked to consider in this example. We know that our Maclaurin series is equal to e to the x for every x. And therefore, we know that this series with term 5 to the n over n factorial is going to converge to the number e to the x with x equal to 5. In other words, the sum of our series is going to be e to the 5th power. If you'd like to try a similar example, pause the video and find the exact sum of the series n equals 0 to infinity of natural log of pi to the nth power over n factorial. You can resume the video in a few seconds and see the full solution. As in the preceding example, if we compare our series with the Maclaurin series for e to the x, namely the series from n equals 0 to infinity of x to the n over n factorial, we see that we can obtain the given series by letting x equal to the natural log of pi. When we make this substitution into our Maclaurin series, we know that this will be equal to e to the natural log of pi, which simplifies to pi using properties of exponents and logarithms.